Okay, this is the retest review for the sequences and series unit. So that's Unit 8. So if you're planning on retaking that test, this is the review you need to be working on. So the first one says evaluate each limit as n approaches infinity. For each sequence, state if it converges or diverges. If it converges, state the number it converges to. Okay, so the biggest difference I want you to notice is here, these are a sub n's compared to like in this number 2, how there's this summation. These are very different. These are sequences. So basically a sequence is a list of numbers compared to a summation, okay, or a series is basically, imagine that same list of numbers, but instead of commas, you're turning those commas into plus signs. So that's the main difference there. Now, that means that for this number 1, you're not going to be able to use this pink sheet because look, it's a summary of test 4 series. These are not series. So all you're doing is evaluating the limit as n approaches infinity. All right, so this is geometric. You know it's geometric because it's a parentheses raised to a power. And what we care about with geometric is that number inside. We call that the R value or the common ratio. In this case, the R value is 5/2, and that's greater than 1, okay? And you're like, oh, well, that's on our sheet. Well, not really. You can still take the limit as n approaches infinity. If you're plugging in numbers, right, imagine what it would be if n equals 1, n equals 2, okay? So if you plug in n equals 1, you're going to have to square both of those. So you're going to get 25/4, okay? And if you plug in n equals 2, that means you're going to have to cube both those. You're going to get 125/8. And you could tell that even that 25 divided by 4, it's not, I know it's not a nice number, but these are going to actually increase without bound. If they are increasing without bound, that's showing that the sequence is diverging. Or you could just say this is geometric. The R value is greater than 1, so this one is diverging. So this one diverges. Okay, it's a geometric where R is greater than 1 and it's increasing without bound. Okay, so it's just going to keep getting bigger and bigger and bigger. It's not going to any one number. All right, here's something that's interesting. At first look, you might not notice that this is geometric. It is indeed geometric because remember, I can rewrite this as 1/4 the entire quantity raised to the n. Okay, because remember, 1 raised to anything is still going to be 1, so this is mathematically equivalent. So now it has that geometric look to it, only this time the R value is 1/4. Well, what do I care about 1/4? I care that 1/4 is less than 1. So you can say that that converges. And what's it going to converge to? Well, think about it. As I increase n here, right, my first term, so at n equals 1, n equals 2. So at n equals 1, I get 1/4. When n equals 2, I get 1/16. At n equals 3, right, 4 to the third power is 1/64. So at n equals 3, I get 1/64. So these are getting smaller and smaller and smaller and smaller. They will never become negative, okay? So you could say that it converges to 0. Converges to 0. Okay, so we've got that one there. All right, let's take a look at this one. Again, when in doubt, you're plugging in numbers. So I'm going to start with n equals 1, n equals 2, and n equals 3. Okay, well, if I plug in n equals 1, that's -1 to the third, which is -1 plus 7. -1 plus 7 is 6. Now I plug in n equals 2. So 2 plus 2 is 4. -1 to the fourth power is 1, plus 7 is 8. I plug in a 3. You're going to get -1 plus 7, which is 6. What's going to happen as n approaches infinity here is this is just going to bounce back and forth between 6 and 8, 6 and 8, 6 and 8. So it's not approaching one number. This is diverging because it's oscillating. Okay, things that oscillate diverge. Diverges. Okay. And remember, if it diverges, you don't have to say what it diverges to. Okay, it just diverges. A lot of times it would be infinity. In this case, it's oscillating, so it's, not diverging to anything. All right. Next, we have this one down here. So right away, I start thinking about L'Hopital's here. you could compare, you could kind of do your limit as n approaches infinity. If you actually wrote that out and this was in August or so, you would say, oh, how do I take limits approaching infinity? You compare the degrees. Here, this is big booty bottom. This is dropping to 0, okay? So you could do it that way. Or you could say, all right, well, the limit as it approaches infinity, right? So if I actually write it out, in these other ones, I didn't actually have to write out the limit as n approaches infinity because I was kind of doing it just by plugging in. But here, the limit as n approaches infinity is a sub n. If I plug in an infinity there and an infinity there, you get infinity over infinity. That's an indeterminate form, which makes it a candidate for L'Hopital. So by L'Hopital's, you still are taking the limit as n approaches infinity. Okay. Well, when I take the derivative, I get 4 over 3n squared. And now when I plug in infinity, I end up with 4 divided by infinity squared times 3 is infinity. Okay, well, a number divided by infinity is 0. So I would say that this converges to 0. And again, could I have gotten that other way? Sure. Converges to 0. Again, I could have gotten that using my, rules from way back in the beginning of the school year, when I know that as I take limits approaching infinity, you could compare the degrees, right? That could work here. If you actually plug in, then it makes it a candidate for L'Hopital's. Or you could have gotten it probably just by, if you plugged in n equals 1, n equals 2, n equals 3, you would see that that's decreasing, but it's not going to be 0 ever, or it's not going to be negative ever, so it's converging to 0 there. Now again, notice that these are all just lists of numbers. There's no plus signs in any of these lists. This is just a sequence of numbers. So that's how you handle sequences of numbers. Okay, next up it says use the integral test to find the upper and lower bounds of the sum. So if I was doing this and it didn't have these directions, I would say, oh, this converges by p series, okay? This is 1 over n raised to a power. That power is 4. And we know from our pink sheet, right, that a p series converges if p is greater than 4. So this converges by p series, but the kind of bad thing about p series is, sure, yeah, you could tell that it converges, but it doesn't tell you what it converges to. Well, I can be slightly less vague, and I can actually do a little better than say, well, I know it converges, but I have no idea. I am going to be able to have an idea by giving an upper and lower bound. But to do that, you need to use the integral test. Now remember, to use the integral test, there is a few conditions that need to be met. It needs to be continuous, it needs to be positive, and it needs to be decreasing. And indeed, 1 over, n to the 4th, it's continuous, because remember, we're plugging in numbers that are greater than 1 there. It's going to be positive no matter what I plug in. As long as n's greater than 1, it'll be positive. And it's decreasing because that denominator is getting bigger, which means overall it is getting smaller, the overall quantity. So because it meets that, it is a candidate for integral test. And the integral test says, I'm going to take the integral from 1 to infinity of that, and instead of writing it as 1 over x to the 4th, I'm going to write it as x to the negative 4th dx, and I just switched it from n's to x's because I'm integrating with respect to x. And once I do that, okay, you can integrate that, so add 1 to the exponent, divide by that number, right, and I'm integrating that from 1 to infinity. All right, and I'm just going to rewrite that, so that's the same. Now this negative can float up to the numerator and be written as negative 1. That 3, though, stays in the denominator. That was a mistake a lot of people made on the test. So that 3 stays in the denominator, and I'm still evaluating this from 1 to infinity. And now I use my fundamental theorem of calculus. So I'm plugging in infinity. I do that in quotes, right? So we're kind of like, all right, if I plug in infinity there, I get negative 1 over infinity minus, because that's what the fundamental theorem of calculus says, it's minus. Now I plug in a 1. When I plug in a 1 here, I get negative 1/3. So it's minus a negative 1/3, which turns to a plus. Okay. Then from there, I can say, well, 1 divided by infinity is 0. 0 plus 1/3 equals 1/3. So this does converge, okay? Now, the integral converges to a third. What does that mean for the summation? Well, it means the summation's going to converge by the integral test. The integral test says that if the integral converges, then the sum converges. What the integral test does not say is that if the integral converges to 1/3, the sum converges to 1/3. Okay, that's not what it says. This 1/3 is important, though. That's actually going to be the lower bound. So when I'm trying to figure out what this sum is, I'm going to say this sum of 1 over n to the 4th. It's going to be between, right? It's bounded, the upper and lower bound. So the lower bound is that 1/3. So that 1/3 goes here. And then what goes over here? Well, I know it's going to be, the sum of this is going to be between 1/3 and 1/3 plus the first term. What do I mean by the first term? I mean, what do you get when you calculate the first term of this? Well, in this case, I plug in a 1, and that's 1 over, well, 1 to the 4th is 1, so it's 1. Someone said, is it always 1? It is a lot of the time, but it depends on what this is. If this n, started at 2, then your first term would not have been 1. So really this is 1 plus 1/3, or you can simplify that and say that that is, 4 over 3. So I know that the sum is going to be between those two numbers, but I cannot tell you exactly what it's going to be, just that it is bounded between those. Okay, this says determine whether the series converges, or diverges, or diverges, state which test you used. Okay, so when I'm doing this one, this is going to be, it's a peak series. It's kind of undercover there. I'm actually going to rewrite that. I'm going to say that that's equivalent, right? It's still the summation from 1 to infinity, but this is going to be the same thing as n to the first times, remember this power over root, this is the same thing here as n to the 1/3. Well, n to the first, when you are multiplying things at the same base, you add the exponents, so I can rewrite that as n to the 4/3, okay? And now that I have that, well, that's going to converge by p series, right? That's a power in this. Here, this is a p. Here is 4 over 3, which is greater than 1. So I would say that this converges by p series. And that's easy enough for me to get some points there. All right, let's see if I can do this last one real quick. All right, when doing this one, I think a lot of people panic because they're like, I don't know what test to use, right? They're like, I don't see a -1. It's not alternating series. Well, I don't see an exclamation point, so it's probably not ratio test either. So you're kind of going through these. I always like to start with the divergence test if I'm not sure, because it's pretty easy to take a limit as n approaches infinity, especially if it looks like something that I want to do L'Hopital's to. That's a good hint that the divergence test might be valid here. So I'm going to take the limit as n approaches infinity. I'm just going to call that a sub n, okay? So, all right, well, when I do that, if I plug in infinity, I get infinity over e to the infinity is infinity. So again, that's an indeterminate form, which makes it a great candidate for L'Hopital's. That's kind of what I was hoping for. So L'Hopital's says I'm allowed to take the limit as n approaches infinity of the derivative of the numerator over derivative of the denominator. Well, the derivative of that numerator is just a 3. The derivative of e to the junk is e to the junk times the derivative of the junk. So we got that there. And now I'm plugging in infinity. So if I plug in infinity there, well, let's see, that gives me 3. If I plug in infinity, e to the infinity is infinity times 2 is an even bigger infinity. So I get 3 over infinity, a number divided by infinity, equals 0. What does that tell us? Well, that was kind of bad news, because if I look at my pink sheet here, the divergence test only works if it equals anything but 0, right? So the divergence test here is inconclusive. Divergence test inconclusive. Inconclusive. So that means you have to try some other test.